Today we're doing recursion, specifically recursion with some memorization or cache. We're going to do that with the example of House Robber 3. The thief has found himself a new place for his thievery again. There is only one entrance to this area called root. Besides the root, each house has one and only one parent house. After a tour, the smart thief realized that all houses in this area form a binary tree. It will automatically contact police if two directly linked houses are broken into on the same night. Given the root of the binary tree, return the maximum amount of money the thief can rob without alerting the police. It's a little bit confusing by what they say by directly linked houses, so let's take a look. Over here we have 3, 2, 3, 2, 1. It's showing that the maximum amount we can rob is 7, which is this one plus this one plus this one. The example you see here illustrate that if you take 3, you cannot take 2 and 3 since they're directly linked. And here you can take 3 and 1 because their parents are not taken yet. Over here the example illustrates the other case. So here you can see that if you take 4, 4 is directly linked to 3, 1, and 3. Since we've taken 4, none of its directly linked members can be taken. So if we take a node, both its parents and children cannot be robbed. The reason why you can tell is recursion is because, well, we have two cases. If we want to know what's the maximum monetary value we can rob if we rob the current house, and what is the maximum monetary we can rob if we don't rob the current house. Now that we know we want to use recursion, we want to find out how we want to traverse the tree. There's two techniques, DFS or BFS. Would both techniques works? Yes, all problems that can be solved by DFS can be converted to BFS, vice versa. But one is going to be very inefficient, right? Let's take a look. If we use DFS, all we need to know is whether or not our parent is taken or not. If our parent is taken, then, well, we cannot use the current node, right? If our parent's not taken, then we have the choice of using this node or not using this node. So what we can do is when we go from 3 to 2, we can pass it down, be like, hey, your parent is used, or hey, your parent is not used. That's how we're going to be using DFS. And then when we go into 3, same thing. When we call upon the right child of 2, we can pass down, be like, hey, 2 is used, or hey, 2 is not used. If that's DFS, right? So DFS, that makes sense. Now let's try it with BFS. So with BFS, we go here, 3, we go 2, okay? We tell it, hey, our parents use or not use, and then we go 3, hey, our parents use or not use, makes sense. And then 3, parents use, not use, makes sense. 3, parents use or not use. So overall, this makes sense. So at this point, both DFS and BFS works. At this point, both algorithm works. It's just like which one is more efficient, right? Well, neither, because we need to optimize it. Why? Here's an example. We have root 3, right? 3, we have the option of take or not take, right? Or like not take. Say if we use take, then we will call upon our child 2. So 2 over here. So before was 3, we're going to call upon child 2. 2 has we have the option. Actually, we have no option. Since 3 is taken, 2 will be not take, right? Not take, and then it will call its child 3. So 3 over here, and then we can choose take or not take, right? Obviously take is better, but we still need to check. So not take. Now we're going to go through take. Now we're going to go through not taking the root. So if we don't take the root 3, we're going to call 2 again. 2 now has the option between take or not take. So take or not take. And then 2 will need to call 3 again. But depending take or not take, it will be called twice. Well, this is not really efficient because when we work on root, we need to go through the take or not take case. That means we need to call its child twice, right? So, but because we call 2 twice for take and not take, each of the time we need to call its child 3 take or not take twice. So in total, 3 is called 4 times, 2 is called twice, and just for one call of 3, the root. this will grow exponentially and will be repeatedly calling its children node over and over again. This is very inefficient. What we can do is when we're done calculating the result for a child, we can cache that result, right? We can cache it. So next time when we go to its child 2, be like, hey, take or not take. For either case, we know the optimal answer. This is how you know you want to use DFS. Reason being is that we will go in depth, know the children first, and at the first hit of 3, we can already cache the result, right? With DFS, we go depth first, cache the result. This way, when the child is called again, we can just use the cache. But with BFS, we don't know the child until we reach that level. We will go 3, 2, 3, and then 3, 1. We will actually call the child last. In this case, so we can't really cache any results. So at this point, we will note that we can solve the problem using recursion, plus DFS, and memorization. After reading the question, I was able to come up with that intuition myself, and that was my train of thoughts. First, identifying that we need recursion, and then deciding whether we use BFS or DFS, and finally, how to optimize it. Here's the code I have created for this question. If the root is empty, there's no houses to rob, we simply return. We have a cache. Like I said, we're going to use some sort of memorization. So here, the key is the node, and for the node, for example, when we land on 2, depending on the case, whether we want to take it or not take it, either way, we can know the max value. And then you can see that I have a single helper function that helps me with the recursion. For the result, we're going to simply return the value of the helper function with our root. The parameter of the helper function is the current node and a Boolean variable. So this is point taken. If it's true, then that means our previous parent, is parent taken, right? So if this is true, that means our parent is taken, then we cannot use our current node. If this is false, that means our parent is not taken, and we can choose whether or not we want to use the current node. So we have 2 values here, take max and not take max. If the node exists in our cache, we can simply update take max and not take max for the current node. If the node is not registered in our cache, we need to calculate it. So first we're going to calculate take max. If we're going to take the node, what is the maximum value? We check what's the maximum value of taking the left side or not taking the left side, either way. Wait, no. So for take max, we actually take the current node, right? So say if 2, we actually take the current node 2. In that case, we pass down with the helper saying that, hey, your parent is taken. If left exists, we go to the left node. Your parent is taken. You cannot use yourself, basically. And for the right node, we do the same. We call helper, indicating that the parent is taken. Now we're going to calculate the not take max. Since we're not taking our current node, then we pass down false, meaning that, hey, your parent is not taken. Once we calculate both take max and not take max, we're going to register it in our cache. Here we have 2 cases. If my parent is taken, say my parent is taken, 3 is taken, then we cannot take the current node. We just simply return the value of the maximum value at this point of the tree of not taking the current max. If my parent is not taken, right, then we have the choice whether or not to take our point or not take our point. We will return the maximum of not taking our point and taking our point. Whichever one is bigger, we're going to return it. And that is the code. Even though the algorithm sounded a little bit complicated, recursion and memorization, but as you can see here, it's relatively straightforward. Now let's talk about runtime and space usage. For the cache, we're going to store every node and its take or max not take value once. So for space utility is on. As for runtime, we're actually only visiting each node once, because once the node is visited, the value is cached. Therefore, the runtime of this algorithm is also on. Just a quick reminder, DFS runtime is on.